Okay, this slide showing liquid vapor equilibrium. Once we hit an equilibrium, it stays steady. We've reached that. This is the point where we hit the equilibrium here. Now, there are two things that are important to this slide. Is that once we hit the equilibrium, does vaporization stop? No. Vaporization never stops. Vaporization continues. The only reason we've hit equilibrium is because the vaporization rate is equal to the condensation rate. It's just spinning in circles, but we can't stop it. This is called a dynamic equilibrium. It's dynamic because vaporization and condensation never stop. Dynamic means motion, but equilibrium means no motion. And so where there's no motion is it's already saturated at 100% relative humidity. The only way we can change that is either by heating it or cooling it. That'll change how much. So that's one important thing. One important thing that you should know: dynamic equilibrium. Another thing that's in this slide is why doesn't vaporization stop? The reason vaporization can't stop because this is what happens. Here. Not all water molecules are moving. This red line here, let's say, is room temperature. And at room temperature, the water molecules don't all have the exact same energy. There's a distribution of energies. And so this is called a kinetic energy distribution. And so water at room temperature, T1, has this kinetic energy distribution. Most of the water molecules have an energy around here. But a small fraction of water molecules have high energy. And there's going to be cutoff. This cutoff is how much energy is required to vaporize. So the molecules below this don't have enough energy to vaporize. The molecules above this have enough energy to vaporize. I should have one more of these curves. There. It'll be easier to look at. And so if we hit this certain energy threshold, then all these molecules are capable of vaporizing. And so there's a small fraction, even at room temperature, this is room temperature, of molecules that have enough energy to vaporize, so they're going to vaporize here. And so vaporization can't be turned off, nor can condensation be turned off, because even at room temperature, there's this fraction. And so how would you describe this curve? This curve just shows the population of water molecules. And so the entire population is represented by this area. Most of the population doesn't have enough energy. And the highest population is here. The highest population is going to have this energy. But we're going to have a whole bunch of water molecules in here. And in that population, there are going to be some that have very high energy. Now, we can shift the energy of that population by changing the temperature. So the blue is actually at a higher temperature. And so what happens is we take that entire population and increase the temperature. If we increase the temperature, it shifts the curve to the right. It also flattens that, so we have more higher energy. And so at higher temperatures, the population increases of higher energy water molecules, and so the rate of vaporization increases here. And so at higher temperatures, we'll have a higher 100% humidity. At lower temperatures, we'll have a lower 100% humidity. And so this is just showing how the temperature affects things. And so this is just showing this here. This is the equilibrium vapor pressure. This is once we've hit 100% humidity. What is that? Well, it depends on the temperature. The higher the temperature, the more the vaporize. And so we have that dynamic equilibrium. Now, once we hit the point where the vapor pressure is equal to atmospheric pressure, that's called boiling point. If it's at 1 atmosphere, we call it normal boiling point. But atmospheric pressure varies. So, for example, at high altitudes, the pressure is lower. In a pressure cooker, the pressures are higher. And so the boiling point changes depending on what atmospheric pressure is. Boiling point is the point at which the vapor pressure is equal to the atmospheric pressure. Under normal conditions, it's 100 degrees C, but in Denver, let's say in Denver, Colorado, the water boils at a lower temperature. In a pressure cooker, the water boils at a higher temperature. The boiling process is overcoming that atmospheric pressure, so here is the boiling process. It's when the vapor pressure going up is equal to atmospheric pressure pushing down. So then we get the boiling curve here. The boiling point is the temperature at which this occurs. Water has an unusually high boiling point because it's got the hydrogen bonding interactions. We'll come back to it. Diethyl ether has a much lower boiling point. All right, so about the dynamic equilibrium, you know, it's dynamic because vaporization, condensation, it's the equilibrium. Equilibrium vapor pressure is once we've hit 100% humidity, what is the pressure of the water molecules? It's a reversible change because vaporization is opposed by condensation. Condensation is the reverse of vaporization. Dynamic equilibrium show that. It's liquid vapor. Okay, there are two other properties I'm going to talk about for water. Viscosity and surface tension. Viscosity is the resistance to flow. So high viscosity means it doesn't flow very easily, like maple syrup. Maple syrup is high viscosity compared to water. Water has a lower viscosity. And so higher viscosity, the more difficult it is to flow. And then we have surface tension. The surface tension is how hard is it to break the surface. Maple syrup, it's a lot harder to break the surface than water, you know. But still, like for example, what's more dense, you know, this plastic or water? I don't know. Actually, that one. But I do know what's more dense, metal or water. What do you think is more dense? Metal or water? Well, let's do steel. What do you think is more dense? A paperclip or water? A paperclip. And so a paperclip should sink, right? If I put this paperclip on water, it should sink, correct? But do you know I could get a paperclip to float? Maybe. I'll try. I'm going to try to get a paperclip to float. See if I can be successful or not. So, you see, I can get a paperclip to float. It should sink. Why doesn't it sink? It's because of the surface tension of the water. The water molecules are held together by hydrogen bonds, right? And you got to break those hydrogen bonds to get the paperclip to sink. So that's surface tension. Surface tension is breaking the surface. It's not so easy sometimes to break the surface. And so this is just showing surface tension. So this is why water droplets, when you look at a water droplet, what's the shape of a water droplet? A sphere. Spheres have the least amount of surface area. And the reason why it's hard to break the surface is because to break the surface, you got to create more surface molecules. Surface molecules aren't as happy as bulk interior molecules. Like a molecule on the surface isn't as happy as a molecule inside. The reason is because a molecule inside has lots more hydrogen bonding than a molecule on the surface. The molecule on the surface is only hydrogen bonded down. The molecule inside is hydrogen bonded in all three dimensions. And so this means that the interior molecule is lower in energy than the surface. And so to create more surface molecules is going to cost you energy. And that cost is the reason why it's hard to break the surface. Does that make sense? And so this is why water droplets adopt a spherical shape. It's to minimize the amount of surface molecules that are present. So what we're going to do is we're going to look at this. All we want to do is we just want to look. As the intermolecular forces become stronger, what happens? As the intermolecular forces become stronger, what happens to the vapor pressure? So let's say strong intermolecular forces, high vapor pressure or low vapor pressure? Low vapor pressure, it's harder to vaporize. And so the stronger the intermolecular forces, the lower the vapor pressure because it's hard to vaporize. The stronger the intermolecular forces, the higher the heat of vaporization or the lower the heat of vaporization? The higher the heat of vaporization. The stronger the intermolecular forces, the more difficult it is to vaporize, therefore it's going to cost you more energy to vaporize. It's going to cost you more heat to vaporize. The stronger the intermolecular forces, the higher the boiling point or the lower the boiling point? The higher the boiling point. The stronger the intermolecular forces, the harder it is to boil. The stronger the intermolecular forces, the greater the surface tension or the weaker the surface tension. So for example, if I try to float a paperclip on water versus maple syrup, what's easier to float a paperclip on, maple syrup or water? Maple syrup, because it's got a stronger intermolecular forces. Versus gasoline. If I try to do this on gasoline, forget it. It's going to be impossible to do it on gasoline because it's weak intermolecular forces. So those are some properties of liquids. So what we're going to do is we're going to take a look at some problems here from our book. So what was the homework I assigned for this particular chapter? Chapter 15. So let's take a look at these problems 1, 3, 5, 11, 19. We're going to do these here in class. Where did that go? Chapter 15. All right, let's take a look at one. A mixture of helium and, oh, this is the wrong chapter, sorry. Oh, no, this is the right chapter. I forgot, I already did this. 1, 3, 5, I jumped ahead. 3, 5, 11, 19, 25. 11, 19, 25. 11. How do intermolecular attractive forces influence the boiling point of a pure substance? So basically this is just asking, the stronger the intermolecular force, the higher the boiling point or the lower the boiling point? Boiling point is the temperature at which it boils. So if you have strong intermolecular forces, they're held together strongly. Liquid is held together strongly. The higher the boiling point. That's it. The stronger the intermolecular forces are, the higher the boiling point will be. The stronger the forces. Okay, that's 11. And then, what was the next one? 19. And then 25. 19. The level at which a duck floats on water is determined more by the thin oil film that covers its feathers than by a body density that's lower than the density of water. The water does not mix with oil, and therefore does not penetrate the feathers. If, however, a few drops of wetting agent are placed in the water near the duck, the poor duck will sink to its neck. State the effect of the wetting agent on the surface tension and intermolecular attractions of water. Do you know what a surface, what do they call it? A wetting agent? A wetting agent is called a surfactant. And a wetting agent weakens the surface tension by interrupting the hydrogen bonds that hold it together. So what happened to the Windex? Do you see the Windex? There it is. Windex is a wetting agent. And so what it does is it weakens the hydrogen bonds that hold it together. So what I'm going to do is I'm going to put a drop of Windex on the inside wall of the beaker and let that Windex dribble down and hit the surface of the water. Watch what happens to the paper clip. This is a magic trick, by the way. Watch what happens to the paper clip when the Windex hits the water. Maybe I'll time it just right. There. Okay, the Windex has hit the water. Let's watch the paper clip. Did you see that? Did you see that? That's because the Windex hit the water and then it started to move over. And then once it got to the paper clip, it weakened the surface tension. Now if I try to float that paper clip, it's going to be impossible to float because my water has been... It's going to be impossible to float this. Do you see that? That's because Windex is a wetting agent. It's a surfactant, and it weakens, and so it makes water not. This is important when you clean stuff. You don't want the water to beat up in balls. You want the water to spread out over the surface. So now this water is going to wet the surface. It spreads out. Versus if I just took a fresh beaker of water, it pools up into pools rather than spreading out into a thin film. And so that's the difference. And so a wetting agent reduces the surface tension of water. So that's exactly what I did. I used Windex to reduce the surface tension of water, overcoming its intermolecular attractions and allowing it to penetrate the duck's feather. The poor duck is going to sink like that, well, like that paperclip did to its neck. All right, 25 is next. Other things being equal, which produces stronger intermolecular attractions? Induced dipole or dipole? What's stronger, dipole or induced dipole? Permanent dipoles or just instantaneous dipoles? Permanent are stronger, so dipole are stronger than induced dipole. What other things being unequal would reverse this order of attractions? What might reverse it is if they're different size molecules. You know, if they're different size, then the dispersion are different. You know, because big molecules have bigger dispersion. Big molecules can generate bigger waves, and those even though those waves are instantaneous. Let's say you have you have a pool like this, big pool, and then you have a tiny pool like this. And the tiny pool has a wave machine, and it's just generating waves, one wave after the other. This is a permanent dipole. But the big pool, even though there's no waves here, if something splashes in here, it can generate a much bigger wave than this can. And so we can't compare pools of different sizes. If we compare pools of different sizes, then the instantaneous waves that can be generated are different. In 2002, a team of scientists discovered that induced dipole forces among millions of tiny hairs on gecko feet and the surface are what allow these lizards to adhere to walls and ceilings. So the walls, in other words, a lizard can hang on to walls and ceilings because of induced dipole. So induced dipole forces can be strong, depending on how big that wave is, or how big the. Other things being equal, dipole forces are stronger. However, induced dipole forces can be bigger than dipole forces when the molecules are very large. That is, we can generate bigger waves in a big pool, even though the big pool might not have any permanent dipole than we can have in a small pool in which waves are continually being generated. Does that make sense? All right, that's 25. Let's go on to 27, 31, 33. 27. What are the principal intermolecular forces in each of the following compounds? Ooh, okay, the first one. You see a hydrogen is bonded to a nitrogen. When you have hydrogen bonded to a nitrogen, we call that H bond. So H bond will be the principal. Here, is this hydrogen bonded to fluorine? No. When we look at CH2F2, what is the structure of that? The hydrogens are not bonded to fluorine. The hydrogens are bonded to carbon. It's not H bonding. This is dipole because carbon-fluorine bonds are going to form a molecular dipole. And it's going to be a permanent dipole like this. So we have a permanent dipole. It's dipole. C3H8. C3H8, that's a hydrocarbon. All hydrocarbons are nonpolar. If it's nonpolar, the only thing is, you got a flat pool like this, the only thing that can happen is if there's an instantaneous dipole, so that would be instantaneous. So we have hydrogen bonding, dipole, and instantaneous dipole. These. Hydrogen bonding, dipole, and induced dipole, right? Instantaneous dipole. What's the reason it's instantaneous? Instantaneous because normally it's nonpolar. Carbon-hydrogen bonds are nonpolar, so if we look at C3H8, look at C3H8. There's no dipole. There's no permanent dipole because the carbon-hydrogen bonds are essentially nonpolar, so this whole thing's nonpolar. So there's no positive end. Is there a positive end to propane and a negative end? There's no positive end, there's no negative end. Whereas in this one, there is. The fluorines are going to be the negative end, the carbon's going to be the positive end. So this has a permanent dipole. This one, there's no, should I call this end negative and this end positive? No. There's no dipole. And so it's got to be instantaneous only. In one instant of time, the electrons are all on one side or the other, or there's a bias, there's more electrons on one side than another, but that's not sustainable. Eventually it's just going to flatten out. We just did 31, 33, 31. Questions 31 through 34. On the basis of molecular size, molecular polarity, and hydrogen bonding, predict for each pair of compounds the one that has a higher boiling point. The bigger the size, the higher the boiling point. The bigger the size because it has more electrons. It's like the bigger the pool, the higher the wave you can generate. So that's it. And so this one's methane versus ammonia. They're both about the same size. What's different is methane is nonpolar or polar? Nonpolar. Ammonia is polar. This is trigonal-pyramidal in shape, so it's polar. And therefore, ammonia should have a higher boiling point because it's got dipole, and methane only has dispersion. Ammonia has a higher boiling point because it has relatively strong hydrogen bonds between its molecules. Actually, I forgot. It's a hydrogen bonded to nitrogen, H bonding, versus relatively weak induced dipoles in methane. So it's even stronger. 31, 35, no, 33. Argon versus neon.
Ammonia would be higher.
Ammonia is going to be higher because of hydrogen bonding interactions. They're both about the same size. So same size pool, but you have H bonding interactions. H bonding interactions. Argon and neon are nonpolar. And so the difference is neon's small, argon is big. Neon has 10 electrons, argon has 18 electrons. Which one can you make a bigger wave with? 10 electrons or 18 electrons? 18 electrons. And so if you have 18 electrons, you can make a bigger wave, which means it's going to have stronger induced dipole or instantaneous. Argon has a higher boiling point because its atoms are larger than those of neon, and thus the strength of the induced dipole forces in argon are greater than neon. 33, 1, 2, 39. Identify the intermolecular forces present in each of the following. Ooh, look at this. The first thing I see is hydrogen bonded to oxygen. Hydrogen bonded to oxygen means hydrogen bonding. So hydrogen bonding, all these have dispersion. Everything has dispersion because we can create waves in anything. B. Do we have hydrogen bonding in B? No. But we do have carbon oxygen. This is going to be bent at 109. That means this is polar. In other words, this is going to be not hydrogen bonding. It's going to be dipole. Dipole, because we're going to have a dipole pointing towards the oxygen. It's dipole. C. Hydrogen bonding, good. D. Hydrogen bonding. That's good. E. No hydrogen bonding. No oxygen, no nitrogen, no chlorine.
Oh,
How can you tell if it's polar or non-polar?
How can you tell? Because carbon-hydrogen bonds are nonpolar. So this whole thing's nonpolar. This is nonpolar, there's no dipole. We can only have dipoles in polar molecules. And therefore, it's nonpolar, meaning that, what's the intermolecular force? Instantaneous induced dipole. So let's check our answers here. Well, what they're saying is in instantaneous induced, you can generate waves in any pool, even if there's little waves being generated. And so we can generate waves here, even though there's a permanent wave. And so instantaneous induced are present in all these. However, E only induced. A through D have the major hydrogen bonding. D, hydrogen bonding. C, hydrogen bonding. A, hydrogen bonding. B is dipole. So here, A, C, D, hydrogen bonding. B has dipole. Dipole, and all these have dipole as well, because of the carbon and oxygen. Here, the O, oxygen hydrogen is hydrogen bonding, the carbon oxygen is dipole. The hydrogen nitrogen is hydrogen bonding, the nitrogen carbon is dipole. That's what they mean by that. 39. I guess that was 39. Chapter 39. 41. 41. Predict which compound, CO2 or CS2, has the higher melting point and boiling point. Explain your prediction. Well, the first thing is we draw out the structure. CO2. Is CO2 polar or nonpolar? It's nonpolar. And so what force holds two CO2 molecules together? There's no dipole, there's no hydrogen bonding. The only thing that's left is dispersion. Book is going to call it induced dipole. I call it instantaneous induced dipole. Instantaneous induced dipole is long, but it's most descriptive. And so if I have two CO2 molecules, I got to count on these instantaneous waves rising up. Well, what about CS2? CS2 is linear like this. CS2 is also nonpolar. And so the only force that's holding these two molecules together will be instantaneous induced. So both of these are instantaneous induced. Are they both going to have the same boiling point? No, we don't know, because which one is the bigger pool? Which one can generate the bigger wave? They're not both the same, because oxygen has how many electrons? 8 electrons. Sulfur has 16 electrons. So sulfur has twice as many electrons as oxygen, which means which one can generate a bigger CS2? Since CS2 can generate bigger instantaneous dipoles, the instantaneous dipole is the wave. Since it can generate bigger instantaneous dipoles, it's going to be the higher boiling point. So CS2, we expect to have a higher boiling point and a higher melting point because it's bigger. CS2 should have the higher melting point and boiling points because its molecules are larger than otherwise similar CO2s. So the induced dipoles are stronger in CS2. That's what the book says.